Hello friends, welcome back to this lecture on relativistic quantum mechanics. In this lecture, we are going to delve into the Dirac's interpretation and the course of his journey through which he reached to antimatter concept. This concept was a very abstract concept in 1928. People were not able to digest even the idea of antimatter. However, Dirac was with full insistence that his equation carries everything meaningful and the negative sign associated with the energy term cannot be meaningless. His conviction proved to be correct after the discovery of positron. Let us delve into the journey. Here in this lecture, we shall roll through the Dirac's struggle for negative energies, his idea of Dirac's sea of electrons, then Pauli's exclusion principle that came for rescue of Dirac in the interpretation, and the Carl Anderson's experiment which awarded him Nobel Prize for evidence of positron. And this Dirac's basis for quantum electrodynamics and particle physics laid a new opening to the subject. I am your instructor, Dr. Shyamkant Anwane, associated with Science College, Nagpur. Let us look more closely at the Dirac's equations problem of negative energy solutions. Here we have started with Einstein's equation of relativistic energy of the particle, and that is in the form E square equal to Pc whole square plus Mc square squared. Now, when you are taking square root on both sides, you are bound to encounter with plus sign as well minus sign. Now, the first part is with positive and another part is with negative. Well, we will go through these equations in normal units where the speed of light appears explicitly. The positive energy solutions have a minimum momentum which is equal to 0. Now you can see this is the base energy level with E equal to 0, and the first positive energy solution, that is the lowest positive energy solution, is E1 equal to mc squared. Higher energy levels corresponds to higher momentum, and the particle, say electron, is moving faster. What is the limit to the energy? There is no limit to the energy. Infinite energy is possible. Obviously, special relativity offers a restriction of c to be the limiting speed, but energy can be infinite. That is allowed. This is allowed by special relativity. As the speed of electron approaches the value of speed of light, that is c, the energy tends to infinity. Suppose an electron has energy E2, that is above the rest energy. It means that the electron is moving with some momentum. It can drop to energy level E1 with the emission of photon. Let us suppose that we are considering electron at energy level E2, and it is then dropping to energy level E1 by emission of a photon, and the energy level E1 is the lowest possible positive energy, which we can call ground state by definition. Then the electron would remain there indefinitely. The negative energy solution is mirror of positive energy solutions. So the highest negative energy will be just below E equal to 0, that we are calling minus mc squared. And in the same fashion, for lower and lower energy levels, minus E2, minus E3 and so on, no upper limit, minus infinity, the momentum is increasing. The highest negative energy is with minus E1 corresponding to zero momentum, an electron at rest. Lower energy states correspond to higher and higher momentum, the electron moving faster and faster, and this continues without limit towards E equal to minus infinity. The existence of negative energy states means that electron with energy E1 can go to the transition energy minus E1 with the emission of photon. From there it can continue falling to ever lower energy states and emitting photons without end. It seems every electron in existence, I mean to say positive energy band I am considering, would fall down this negative energy ladder, emitting an infinite amount of radiation in this process. Thankfully, this doesn't happen, but it makes Dirac's equation as it stands unviable. So here you can see when electron jumps from energy level E2 to energy level minus E1, it will emit a radiation of frequency given by the formula. So this unending process is fortunately not happening, but this leads Dirac's equation towards unviability. Dirac came out with this idea in a different way that we'll see in the next slide. In the year 1929, Dirac submitted a work around to this problem in a paper entitled A Theory of Electrons and Protons. In this section subtitled Solution of Negative Energy Difficulty, after noting the problem, he offered a solution. It is like the Pauli's exclusion principle, however, will come into play and prevent more than one electron going into any one state. Let us assume that there are so many electrons in the world that all the states of negative energy are occupied except perhaps a few of small velocity. We shall have we shall have an infinite number of electrons in negative energy states, and indeed an infinite number per unit volume all over the world. But if their distribution is exactly uniform, we should expect them to be completely unobservable. Only the small departures from exact uniformity brought about by some of the negative energy states being unoccupied, we can hope to observe. Dirac went on to suggest that these unoccupied negative energy states might actually be protons. So Dirac says, yes, there are an infinite number of negative energy electron states, but they are all full. And the infinite number of electrons that fill them are invisible. They have no observable effect. It's hard to overstate how this particular situation is sounding this idea. As far as the negative energy states go, it's invisible electrons all the way down. So within a few millimeter sized region of space, There are an infinite number of electrons with velocities ranging from 0 to arbitrarily close to velocity of light. Yet, we can't see them or otherwise observe any effect due to their presence. This explanation became known as Dirac sea. Needless to say, it is controversial and was the target of serious criticism in the opinion of Werner Heisenberg, who quoted that the saddest chapter of modern physics is the remains of Dirac theory. I regard it as a learned trash which no one can take seriously. Here's the things about science though, ultimately people's opinion don't matter. It doesn't matter even if the idea seems ridiculous or even laughable. There is only one scientific authority, that's nature, and you can go in the laboratory and verify the things. What matters is an idea that leads to testable predictions, and if those predictions can be verified. Dirac supposed that just as negative energy electrons could emit photons, they could also absorb them. Therefore, photon of energy twice mc squared, you can identify in the diagram, could cause an electron to transition from highest negative energy state to lowest positive energy state. Half of the energy mc squared would correspond to the mass m of the electron, and the other mc squared would correspond to the mass. Moreover, taking a negative charge away from nothing would leave a positive charge. Dirac called this empty negative energy state a hole and predicted it would behave like a particle with electrons, mass and opposite charge. Here's a cartoon representation of the prediction. The electron in the box represents invisible Dirac sea. On the left, a photon excites one of the Dirac sea electron into a positive energy state wherein it becomes visible. This leaves a hole in Dirac sea. The energy of the system has increased by twice mc squared. The electric charge has not changed because we have merely changed the state of pre-existing electron. Dirac's claim, shown in right, is that this will appear the same as if it created two particles with positive energy, an electron and a positively charged particle with the same mass as the electron, which for now we'll call positive electron. The energy of this system has also increased by twice mc squared and the charge is unchanged. Since we created both negative and positive charges, will cancel out. Suppose the electron above the hole moves downwards. In fact, the hole has moved upward. At right, this would be equivalent to positive electron moving upward. As this continues, what we would observe is positive electron moving through space. In 1931, Dirac submitted his predictions for publications. For publication, he claimed a hole, if there were one, would be a new kind of a particle unknown to experimental physics, having the same mass but opposite charge to that of electron. We may call such a particle as anti-electron. Presently, we are calling that as a positron. As there you have prediction of antimatter. There was no experimental evidence for existence of such bizarre thing in that era. This motivated solely, one might say, by Dirac wanting to fix something shortcoming of his equations. He continued, we should not expect to find any of them in nature on account of their rapid rate of recombination with electrons. But if they could be produced experimentally in high vacuum, they would be quite stable and amenable to observations. So, according to Dirac, it should be possible for energy of photon to be transformed into an electron and anti-electron pairing. The electron and anti-electron can be distinguished by applying a magnetic field which causes moving charges of different signs to curve in opposite direction. In 1932, Carl Anderson was using the so-called cloud chamber to observe cosmic rays. A charged particle traveling through a cloud chamber ionized molecules along its path. Those ions then cause a supersaturated vapor in the chamber to condense into a visible cloud of droplet. The result is to make particles track through the chamber visible. 1936 Nobel Prize winner Carl Anderson performed an experiment for which he was awarded Nobel Prize, and this experiment was the first direct experimental evidence of positron, that is antimatter. A photon of energy twice mc squared, where m is mass of electron, is traveling, and it gives birth to positron and electron, both being negatively charged when subjected to external magnetic field tracks opposite path, you can observe. In 1929, Dirac submitted a work around this problem in a paper entitled A Theory of Electrons and Protons. In the section subtitled Solution of Negative Energy Difficulty, you can observe on your screen, he mentions we shall have an infinite number of electrons in negative energy states, and indeed an infinite number per volume all over the world, but if their distribution is exactly uniform, we should expect them to be completely unobservable. Still, there is something strange about Dirac's idea of sea of electron, which is often called in the literature as Dirac's sea. Here you can see the cartoon representation for this. This is the energy level E equal to 0, then energy level minus E1, minus E2, minus E3, minus E4, minus E5, so on up to infinity. Now, these all levels filled we are considering. So, a photon is falling, and that is taking electron to positive energy state. In this cartoon representation of Dirac sea, as a place to first pull out electron is appearing, and at the second place something whole that is created or existing. This is what Dirac's equation predicts. In the new cartoon, there's no need for consideration of Dirac's sea. We simply create electron hole pair, and this is what is experimentally observed. So here in this animation you can see a photon coming, and this creates a pair of particle by disappearance, and an electron hole pair is generated. Isn't this more elegant explanation? It doesn't require space to be filled with an infinite number of invisible negative energy electrons. So why can't the theory predict that directly? The problem is with quantum mechanics itself. We'll see in the next slide. Here on the left hand side you can observe a cartoon representation of sea of electrons. That is the idea of Dirac, wherein all negative energy electrons which are infinitely large in number and not visible are being represented. Some of it gains energy and comes into the zone of positive energies, thereby creating back a vacancy that was called hole that time. In the new cartoon, you can observe on right hand side that there is no need for Dirac sea. We simply create an electron positron pair. This is what is experimentally observed. Isn't this a more elegant explanation? It doesn't require space to be filled with an infinite number of invisible negative energy electrons. So, why can't the theory predict that directly? The problem is with quantum mechanics itself. We'll see in the next slide. The biggest question at this moment is why can't the theory predict direct creation of electron positron pair at this point? The problem lies with quantum mechanics itself. First, we started with the assumption that psi is the wave function for a single electron. There's nowhere for other particles to fit into the theory. Secondly, in both Schrodinger's equation and Dirac's equation, probability at any point of time that the electron is somewhere present in the space is always 100%. Therefore, projecting this back in time that it cannot be created, it can never be created, and projecting it into the future that it can never be destroyed. It follows that if electron appears, it must have actually already existed and merely transitioned from invisible state to the visible state. And if it disappears, it must have merely transitioned to invisible state in which it still exists. The Dirac sea provides the required invisible state, and it provides a way to account for the properties of positron as a whole in the Dirac sea in the theory that only describes electron. What in time became more clear is that, to quote Steven Weinberg's relativistic wave mechanics, in the sense of relativistic quantum theory of fixed number of particles is an impossibility. Another theoretical framework was needed to express these ideas. Eventually, quantum electrodynamics, the first quantum field theory, was able to recast Dirac's equation into the formalism that gives a rigorous and coherent description of electrons, positrons, photons and their interaction without negative energies and without Dirac's sea. So this is the point where we conclude our discussion about the derivation of Dirac's equation and its interpretations and predictions. On your screen, you can observe Dirac's equation in different forms. And here it is the point where the quantum field theory comes to rescue us and develop it towards the particle physics, which is believed to be the most successful theory of present times. So here we are done with our discussion. Thank you very much for your interest and attention. Your feedback about this course is very valuable to us. You can write down your expectations also for future course. Thank you very much.